In this lecture, we continue our discussion on vehicle routing problems. We address the single depot vehicle routing problem as mentioned in the earlier lecture. So, there is a single depot which we may call as D, and there are a set of customers, and let us assume that there are 6 customers. Let us call them 1, 2, 3, 4, 5, 6. Now, more than one, at least 2 vehicles will move from this depot and will transport goods to meet the requirements of these 6 customers. We can consider the case where the vehicles or the trucks have a capacity and there is a requirement in terms of quantity from these places. We can also look at the case where we do not explicitly consider the vehicle capacity and the requirement. If there is only one vehicle, as mentioned in the earlier lecture, now this vehicle will move from the depot, visit all these places once and only once and come back to the depot, and then the vehicle routing problem reduces to the travelling salesman problem, which we have seen in the earlier lectures. Now, in order to have a vehicle routing problem, we assume that there are at least 2 vehicles, are required. As mentioned, there are 2 cases. One, the case where we look at capacity of the vehicle and requirement of these places. The second, we do not look at the capacity, we only look at the movement or distance that these vehicles have to cover. If we consider 2 vehicles, one feasible solution would be that vehicle 1 can start from the depot, go to 3 and then to 4, then to 5 and then come back to the depot, while the other vehicle can start from the depot, go to 2, go to 1, go to 6 and then come back to the depot. We may call this as the route for vehicle 1 and this for vehicle 2. Now, the problem is which are these out of these 6 cities? If we consider 2 vehicles, which are these cities or nodes that will go to each vehicle, and what is the order in which the vehicle will move such that the total distance travelled by both the vehicles is minimized. So, this is a feasible solution. D 3, 4, 5, D is a feasible solution, and D 2, 1, 6, D, this represents a feasible solution for 2 vehicles. Therefore, the vehicle routing problem actually comprises of 2 problems. The first problem is like an allocation problem, which says which of these customers will go to which vehicle, and the second is a routing problem, and what is the order in which the vehicle will move such that it travels minimum total distance. Now, let us explain this vehicle routing problem with a numerical illustration. The data is shown in this table. Now, here we have a 0 and then 1 to 6, 0 and 1 to 6. 0 represents the depot. 0 represents the depot, which means that, and these 6 represents the node or the cities. Therefore, 0 to 120 means that city 1 or node 1 is at distance d equal to 20 from the depot. D02 being 18, it is like saying this distance is 18. Now, 1 to 2 is 22, 1 to 6, 1 to 2 is 22, 1 to 6 is 28, 6 to 1 is 19, D to 3 is 14, 3 to 4 is 20, 4 to 5 is 30, d to 5 is 12. So, we might say that for this feasible solution the total distance travelled would be 14 plus 20 34, 34 plus 30 64, 64 plus 12 76, and 18 plus 22 40, 40 plus 28 68, 68 plus 19 is 87, and the total distance travelled is 163 for this feasible solution. The optimization problem is which of these cities will go to which vehicle and what is the order in which these vehicles will move. Now, this is an example where we have not explicitly considered the capacities. Now, let us try to impose these capacities and check what happens to the solution. Now, if we look at Q equal to 4 6 3 2 3 2 and capital Q equal to 10. So, what do these mean? Now, here we are going to bring capacity into the picture. Now, this means that these 6 vertices 1, 2, 3, 4, 5 and 6 require 4 units, 6 units, 3 units, 2, 3 and 2 respectively. These could be tons of some material that have to be delivered and so on. Now, this capital Q equal to 10 would mean that the vehicle that takes this material has a capacity of 10. Now, the moment we bring in this capacity and try and obtain a feasible solution, we have to see that the allocations satisfy the capacity constraints. Please note that this feasible solution has been arrived without considering the capacity. Now, let us check whether 1, 2 and 6, if a vehicle starts from D, goes to 6, then to 1 and then to 2, then the capacity that is required from the vehicle is 4 plus 6 10 plus 2 12. Now, the vehicle has capacity equal to 10. Therefore, if we bring in the capacity conditions, then D 6 1 2 is not feasible. Now let us look at 3, 4 and 5. 3, 4 and 5, the capacities are 3 plus 2 5 plus 3 8. The vehicle has a capacity of 10. So, this part of this is feasible, but the overall solution is not feasible because this violates the capacity restriction. The moment we also bring in capacities, we can do further computation and say that the total demand of the 6 nodes are 4 plus 6 10, 15, 20. The capacity of the truck being 10, we would say that minimum number of trucks required is the upper integer value of 20 by 10, which is upper integer value of sigma q by q, which happens to be 2 in this case. And by looking at these, the only possibility that can happen is 1 and 2 will go to one vehicle and 3, 4, 5, 6 will go to another vehicle. Now, we may consider an allocation which is like this: D 1 2 D, D 3 4 5 6 D. Now, this satisfies the capacity restrictions also. So, D 1 2 D will now have D to 1 is 20, 1 to 2 is 22, 2 to D is 18. So, this will travel distance equal to 60. D to 3 is 14, 3 to 4 is 20, 4 to 5 is 30, 5 to 6 is 26 and 6 to D is 19. So, this will be 34, 64, 70 plus 20 90 plus 19 is 109 and the total becomes 169. Now, we realize that if we bring in the capacity constraints, this solution which was feasible otherwise becomes infeasible, and then we may have to look at another feasible solution. Now, the decision problem or the optimization problem here would be, what is the allocation to each vehicle, what is the route it takes, such that the distance travelled is minimized, which is the objective function, and these constraints are satisfied. So, if we look at only distance, then the problem is a normal vehicle routing problem, which optimizes only the distance. If we also look at capacity, we also add capacity constraints into the vehicle routing problem. So, first let us try and solve the vehicle routing problem only for the distance, initially ignoring the capacity constraints, and then we look at methods which also include the capacity constraints. Now, there is obviously a strong relationship between the vehicle routing problem and the travelling salesman problem, assuming that we are not looking at the capacity at the moment. So, we are looking at solutions which are similar to this, and we are not worried if these violate the capacity restrictions, because at the moment we are not considering the capacity restrictions. So, there is a strong relationship between the vehicle routing problem and the travelling salesman problem, because the second part of the vehicle routing is actually a TSP. Now, it is like saying, this solution is like saying, I have already allocated 1, 2 and 6 to one vehicle, 3, 4 and 5 to another vehicle, and once I have done the allocation problem, I can solve 2 TSPs to find out what is the best route that it takes, such that the total distance is minimized. So, there is a strong relationship between these two problems, and therefore, we try and see if we can get solutions to the VRP that are based on solving travelling salesman problems. Now, in order to do that, let us assume, to begin with, let us assume we can now solve the vehicle routing problem as mentioned in the earlier lectures in 3 different ways. One is, I give a certain number of vehicles, so use given number of vehicles, that is one, and second problem would be to use enough vehicles that minimize distance. And third, of course, is to use minimum number of vehicles. The minimum number of vehicles comes when the minimum number is computed with capacities in mind. Since we are right now not looking at capacities, we restrict ourselves to these 2 types of problems, where given a certain number of vehicles, we try to find out what is the best solution. Second, given a certain number of vehicles, if there is a solution that uses fewer than the given number and yet minimizes, can we find such a solution. So, both these we look at, and we try to apply ideas of the travelling salesman problem to solve the vehicle routing problem. So, let us consider n equal to 4, which means we are looking at 4 vehicles maximum, let us say, that are available. So, we now construct a 10 by 10 travelling salesman problem. So, we construct a 10 by 10 travelling salesman problem, where we call 1, 2, 3, 4, 6, so this is a 10 by 10 problem, where 7, 8, 9 and 10 correspond to vehicles, and these correspond to the cities. Similarly, these are the cities and these are the vehicles. Now, this is going to be a distance matrix. So, right now we have a city distance matrix, which is given by this portion of the table. So, we go back and write the city distance matrix. So, we get dash 22, 18, 30, 26, 28, 22 dash 32, 20, 22, 21, 18, 32 dash 20, 22, 21, 30, 20, 20 dash 30, 22, 26, 22, 22, 30 dash 26 and 28, 21, 21, 22, 26 dash. So, this is the 6 by 6 distance matrix. Please note the symmetry. Here only one part or the upper triangular portion of this matrix is shown. This matrix is symmetric, therefore, whatever we see here as 18 appears as 18 here. Now, let me temporarily partition this into 4 areas more for understanding and clarity. So, this part of the table we have already filled. Now, 7, 8, 9 and 10 are vehicles, but 7, 8, 9 and 10 right now are sitting at the depot. So, distance between 7 to 1 is nothing but the distance between the depot and city 1. Similarly, distance between 7 and 2 is the distance between the depot and city 2 and so on, and therefore, 20, 18, 14, 16, 12 and 19 actually represent 20, 18, 14, 16, 12 and 19 represent the distance between 7 and 1, 2, 3, 4, 5, 6. Now, 8 is another vehicle which is still sitting in the depot, and therefore, the distance between 1, 2, 3, 4, 5, 6 and 8 is the distance between 1, 2, 3, 4, 5, 6 and the depot. Therefore, this column repeats again. In fact, this column is repeated 4 times or as many times as the number of vehicles that we are considering. Now, again because of symmetry, it is fairly obvious that this portion will come here as well. So, we write now, what are we going to do with this 4 by 4? Now, if we have to use all the 4 vehicles that we have, let us try and get a feasible solution that uses all 4 vehicles that we have. A simple feasible solution would look like this: D 1, 2, D, 3, 4, D, 5, D, 6, D. Now, this is a feasible solution, which means that vehicle 1 starts from the depot. So, this is vehicle 1, goes from 1, 2 and back to depot. This is for vehicle 2. Vehicle 3 covers only city 5, vehicle 4 covers only city 6. Now, this is a feasible solution that involves 4 vehicles. Now, let me write another solution and let us check how many vehicles that solution requires. Suppose we write D 1, 2, 3 D, 4, 5 D, 6 D, D. Now, this means one vehicle goes to these 3, one vehicle goes to these 2, another vehicle goes to this, and the 4th vehicle does not go anywhere, it goes from the depot to the depot. Now, this means effectively that there are only 3 vehicles. So, if we want a solution with 4 vehicles, except for the last, we should not have 2 depots coming nearby. If you have a D assignment, then it means that you actually are not using a vehicle as shown here. The only place where you can have, you always have to end with a depot. So, this one does not have any 2 D's coming next to each other. Now, this one has 2 Ds coming next to each other, therefore, this means you are using one vehicle less. Here it means you are using all the 4 vehicles. So, in order for a solution to use all the 4 vehicles, we should not have a D-D assignment. Since we do not have a D-D assignment, what we have to do here is you put infinity all over. This dash represents infinity, and because these values are infinity, you will not have a D-D assignment. So, if we want to use all the given vehicles, then what we need to do is to put infinity in this portion of the matrix, and then we can solve a traveling salesman problem out of this. Now, we are not going to solve a 10 by 10 in this lecture stepwise, we are only going to show the solution as such. So, let us now solve this problem using a branch and bound algorithm. So, the first thing that we know is sum of the row minima is a lower bound to the TSP. So, what is the sum of the row minima? We get 18 here, 18 plus 18 is 36, 36 plus 14 is 50, 66 plus 12, 78, 78 plus 19 is 97, 97 plus 12 is 109, 109 plus 12 is 12 and another 12. So, 109 plus 48 is 157, which is the row minimum that we have here. So, row minimum is 157 for this. So, let us repeat it again. So, 18 plus 18 36, 50, 66, 78, 78 plus 19 is 97, 97 plus 48, 97 plus 48 is 145 is a lower bound to this. So, we could say that the lower bound is 145 to this. We can actually update the lower bound further by also doing the column minimum subtractions, and if we do the column minimum subtractions and if we add that to 145, we will start with a lower bound of 164. The row minimum subtractions lead us to 145, the column minimum would give us, after doing this row minimum, now every row has 1 0, then we need to check if all the columns have a 0. If the columns do not have a 0, then we subtract the column minimum from this and the lower bound will now become 164. Then we can go back and try to find the penalties as we did in the branch and bound, and when we do that, we realize that 1 to 2, branching on 1 to 2 is the one that has the maximum penalty, and the maximum penalty turns out to be 2. So, the lower bound will get updated to 166. We are also going to show in this case that if we consider a solution which is like this, D2 1 3 D4 D5 D6 D. If we look at a solution like this and try to find out what is the distance associated with that. Now, D to 2 is 18, D to 2 is 18, 1 to 2 is 22, 1 to 3 is 18, D to 3 is 14, D to 4 is 16, 4 to D is 16, D to 5 is 12, 5 to D is 12, D to 6 is 19 and 6 to D is 19. So, the distance travelled would be 18 plus 22 40, 58, 72, 88, 104, 116, 128, 128, 147 plus 19, which is 166. So, this is a feasible solution with value 166. In our branch and bound, we started with the starting lower bound of 164 and we branched with x12 equal to 0 to get 166. Now, here also when we branched we got 166. Now, we have a feasible solution with z equal to 166. So, we can fathom this node by feasibility and we can fathom this node by lower bound greater than or equal to current best upper bound. This will become the current best upper bound with solution equal to 166. So, the lower bound being 166, we now terminate the algorithm by saying that this solution is optimal for the case when we want to use all the 4 vehicles. The actual solution will be, there is a depot here. So, one vehicle will go from the depot to 2 to 1 to 3 and come back. There is another one which will go from depot to 4 and come back. There will be one that will go from depot to 5 and then there is one that will go from depot to 6 and come back. Please note that solving this 10 by 10 problem from the beginning would take a lot of time, and in order to save time we follow this here. Ordinarily we should have got this 164 as 145 plus 19, 145 obtained by subtracting the row minimum and 19 by the column minimum. After we subtract the row minimum and column minimum, as we did in the branch and bound method earlier, we will then have a matrix which has a 0 in every row and every column, and for every 0 that is present in the reduced matrix, we will find the row penalty and the column penalty and we add, and then we pick that 0 which has the highest value of the sum of the row penalty and column penalty, and that turns out to be x12 with sum of the row penalty and column penalty equal to 2. Therefore, when we branch on x12 equal to 0 and x12 equal to 1, the lower bound gets updated from 164 to 166. Now, here having made the assignment, then we leave the first row and the second column, and then we have a resultant 9 by 9 matrix, and then we also put x21 equal to 0, put a dash there, and then verify whether every row and every column has a 0. Now, we will observe that one of the rows or columns does not have a 0, therefore, we have to do a subtraction and we would subtract 2, so that the lower bound gets updated to 166 here. Here also the lower bound gets updated to 166. Now, ordinarily in the branch and bound algorithm, we should have proceeded further, and only after 10 more levels or allocations we would get to the optimal solution. But just to show the concept of the branch and bound, we picked up a feasible solution here, and since this feasible solution is an upper bound by itself with value 166, we can now terminate this based on feasibility, and we can also terminate this based on the lower bound being greater than the current best upper bound. Here also lower bound is greater than or equal to current best upper bound. This is the current best upper bound. Ordinarily in the branch and bound algorithm, there are several steps here before we would actually reach this solution, but then we have, to save time, we have ignored those steps, we have only taken the solution, and we show here that this solution is optimal. This actually also leads us to a very interesting point, that whenever we solve either a TSP or any of these difficult problems optimally, it is a good idea to have some feasible solutions at different points in time, so that every time a lower bound is increased, we can compare whether the lower bound is greater than or equal to the current best upper bound, and if it is greater than or equal to the current best upper bound, then this node can be fathomed. So, we have now got the optimal solution to this, and this will be the allocation for the vehicle routing problem. Let us also check, remember that this matrix does not consider the capacities, this considers only the distance, and therefore, a solution of this type would mean that we are looking at only distance and we are not looking at capacity. Now, can we see whether this is okay even with the capacities? Now, the solution is 1, 2, 3, 4, 5 and 6. Now, we realize 1, 2, 3 would require 13, 4 requires 2, 5 requires 3, 6 requires 2, but the capacity is 10. Therefore, this solution is not feasible to the capacity case, and therefore, is not optimal to the capacity case. Then what do we do to the capacity case? Then when we actually do the branching, every time we add variables here, we need to verify whether the constraint is satisfied. So, the branch and bound becomes a little more involved when we also bring in the capacity constraints. If we look at the uncapacitated case, where we are interested only in minimizing the distance, then this is a way to get the optimal solution to the VRP for a given number of vehicles. Also note that branch and bound can become very time consuming and can also become memory consuming. So, it can become both laborious in terms of effort that is required to solve, it can also become very tedious to finally solve this. And we have already seen that branch and bound algorithms are worst case exponential algorithms, and therefore, may give the exact solution, but after an exponential number of iterations or after a considerably large number of iterations. Therefore, we have to move towards heuristics to solve the vehicle routing problem, but before we move to the heuristics, we will also look at the second case that we described, that can we use enough vehicles which is less than or equal to the given n such that I may get minimum distance, which simply means that I have 4 vehicles. This is an example of a feasible solution with 4 vehicles. This is an example of a feasible solution with 3 vehicles. Now, let us calculate the distance associated with this and distance associated with this. So, d1 to d will be, d to 1 is 20, 1 to 2 is 22, 42, and 2 to d is 18. So, this is equal to 60. d 3 4 d is, d to 3 is 14, 3 to 4 is 20, 34, 34 plus 16 is 50. Now, d 5 d is 0 to 5, so 24, 12 into 2, and this is 38. So, this would have a total distance of 110, 134, 142 plus 30, 172. So, this is a feasible solution which would give 172. Now, we are not looking at the capacity. So, this is another feasible solution with 3 vehicles. Now, let us find out the distance for this. So, d to 1 is 20, 1 to 2 is 22, 42, 2 to 3 is 32, 42 plus 2, 44, 74, 74 plus 14 is 88. d 4 5 is 16, 4 to 5 is 30, 46, 46 plus 12, 58, and d 6 d is 38. So, this is 24, this is 184. So, this turns out to have a higher distance compared to this, but it may also be possible for us to find another solution which with 3 which may have a distance less than this 172. For example, if we look at a solution d 4 to If we look at the other solution D213, D4, D5, 6, D. If we look at this solution and D, now this is a solution which uses 3 vehicles. One vehicle uses 213, one vehicle uses 4 and one vehicle uses 5 and 6. So, D213 will now be 18 plus 22 plus 18 plus 14, D22 is 18 plus 22 plus 1 to 3 is 18 plus 14. So, D to 2, 2 to 1, 1 to 3, 3 to D will involve 40, 58 plus 14, 72. D4D would be 32, D to 5 is 12, 5 to 6 is 26, 38, 38 plus 19 is 57 plus 57. So, this would give us 2 plus 2 4 plus 7 11, 6 plus 3 9 plus 7 16. So, this would give us a solution which is less than this. So, the point we are trying to make here is we solved a problem with 4 vehicles and in fact, we got the optimum solution to be 166. Now, in the same case we have a feasible solution with 3 vehicles which has 161, which is less distance than 166. So, the optimal solution with 3 should have 161 or less. So, the next problem is given 4 vehicles, if there is the best solution that has a total distance less than the 166, then what is that distance, what are the corresponding number of vehicles that we use and what is the allocation. So, that is the next question that we will address, and can we address this with the same matrix. Now, one way to do is to say that I solve it for 2 vehicles, I solve it for 3 vehicles and then take the best. The other is to do this. You could simply put zeros here in the off diagonals. So, you put zeros in the off diagonals, which means we allow the D to D allocation that comes in, which is like this. So, which means we can consider a 4 city allocation, we can consider a 3 city, a 4 vehicle, a 3 vehicle, a 2 vehicle, even a single vehicle we consider, and in all these 4 whichever gives the minimum value we can get out of this. So, by solving the same 10 by 10, but by replacing these m's or dashes with 0, we can get the best value which would be lesser than or equal to 166, which may use 4 or lesser number of vehicles. Therefore, both the problems that we looked at here, to solve for a given number of vehicles and also to find out the best number of vehicles which is less than or equal to a given number that we have, to find out that best number and the best distance and the best allocation. So, both these problems can be solved using the TSP approach by suitably changing only this portion of the TSP matrix. Nevertheless, whatever we mentioned about the TSP holds good. The TSP being a difficult problem to solve, solving the vehicle routing problem using the TSP idea can give exact solutions to small sized problems, but as the problem size increases, it becomes much more difficult to solve the TSP optimally. Therefore, we move to looking at heuristics that can solve the vehicle routing problem. Now, in this lecture series, we will look at 2 heuristics that will solve the VRP. Now, let us go to this heuristics. Now, let us consider a situation where there is a depot D and we are considering only 2 cities or 2 places 1 and 2. if we have two vehicles, one of the things we can do is we can send a vehicle from the depot to 1 and then come back, and we can send the other vehicle from depot to 2 and comes back. It need not even be two vehicles. The same vehicle may first go from depot to 1 and then come back, and then go from depot to 2 and then come back. In such a case, the distance that this vehicle will travel will be d01 plus d10 plus d02 plus d20, which means distance between the depot and the vehicle twice, distance between the depot and the second city twice. So, this will be 2 times d01 plus d02, where these two are these distances. Now, if we choose to combine these two, which means a vehicle starts from the depot, goes to 1 and then it goes from 1 to 2 and then it comes back from 2 to the depot, then the distance that it will travel will be d01 plus d02 plus d12, d01 plus d12 plus d02. Now, if it turns out that this is higher and this is lower or smaller, then by combining these two we save some distance. So, we call the saving is this minus this. So, this will be d01 plus d02 minus d12, because we are subtract, this is 2 times d01 minus d01 is d01, similarly this and subtract. So, if we change this 1 and 2 to I and j, then for any given two cities, saving Sij will be equal to d naught I plus d naught j minus dij. Now, again this saving can be positive, this saving can be 0, this saving can be negative. Now, this saving will be positive when this quantity is bigger than this quantity. This saving will be 0 if both of them are equal, and this will be negative if this quantity is smaller than this quantity. Ordinarily, distances satisfy triangle inequality, which means dij plus djk is greater than or equal to dik. So, if distances satisfy triangle inequality, then this will always be greater than or equal to this, and therefore, Sij will always be greater than or equal to 0. So, it is customary to use the Sij and try to find out what can be the saving if I combine I and j together. Now, we can compute the Sij matrix from this, because the d naught I and d naught j are given here and the dij's are given here. So, we have 6 cities and therefore, we will have 15 values for Sij. This is expected to be a symmetric matrix. So, we get 6 into 5 by 2 or NC2, Ij can be chosen in NC2 ways. So, which for n equal to 6 will give us 15, which is d naught 1 plus d naught 2 minus d12. So, from this table d naught 1 is 20, d02 is 18. So, 20 plus 18 is 38, d12 is 22. So, this is 38 minus 22, which is equal to 16. So, every Sij can be calculated because we know the d naught I as well as d naught j from here, and then we also know that the dij can be obtained from this. So, we can calculate all the Sij's. Since the depot is denoted by 0 and there are 6 particular cities, then we have for Sij we have 6C2, which is 15 values of Sij. So, these 15 values are computed and they are shown here. So, for 1 to 2 the saving is 16, 1 to 3 the saving is 16, 2 to 6 saving is 16, 2 to 4 saving is 14, 3 to 6 saving is 12, 1 to 6 saving is 11, 3 to 4 saving is 10, 2 to 5 is 8, 1 to 4 6, 1 to 5 6, 5 to 6 5, 3 to 5 4, 4 to 6 3, 2 to 3 it's 0, 4 to 5 it's minus 2. Let us quickly verify some of these calculations randomly. Say let us take 3 to 6. So, D03 is 14, 06 is 19, 19 plus 14 is 33 and 36 is 21. So, 33 minus 21 is 12. So, let us quickly check here for 2 3, 02 is 18, 03 is 14, 32 and 2 3 is 32 which gives us 0. So, let us do it for 4 6, 04 is 16 plus 19, 35, 35 minus 32 is 3. So, this way we have calculated the Sij's and we have kept it here. The minus value here, the negative value here for Sij indicates that this system does not satisfy triangle inequality. We have already seen that if it satisfies triangle inequality, Sij is greater than or equal to 0. Now, with these savings, let us try and compute the solution based on the savings algorithm. So, now and we have already arranged these 15 savings in decreasing order starting from 16 going up to minus 2. So, we start with the saving 1 to 2, which means cities 1 and 2 can be combined together in the same route. So, 1 to 2 gives us a saving of 16. We also know that this requires a load of 4 plus 6 10 and the total capacity is 15. So, we could use 1 to 2, put them into the same vehicle and have a saving of 16. Now, the next saving is 1 and 3. So, 3 has to go here, but if we put 1, 2 and 3, it is 4 plus 6 10 plus 3 13. So, we could use 1 3 and get a savings of another 16. The next one is 2 6. We already have 1 2 and 3 put together. So, 1 2 3 and 6 exceeds the available capacity of 15. So, we cannot use 2 6. Similarly, with 2 4, 1 2 3 already here plus 4 exceeds the capacity of 15. So, we cannot use this. 1 3 6 again we cannot add because we already have 1 2 3 together. Adding another 6 is going to exceed this capacity. Same can be said of 1 6, same can be said of 3 4, same can be said of 2 5, same can be said of 1 4, same can be said of 1 5. Now, the next thing is 5 6, 5 6 do not appear here. So, 5 and 6 can be taken together to 5 and 6 can be taken together to give us a saving of 5. 3 and 5 cannot go together because 3 is in this vehicle, 5 is in this vehicle. 4 and 6 can go together because already 5 and 6 are here. 5 and 6 uses 9 out of this 15, 4 can be added. So, 4 and 6 gives us a savings of 3. Now, we have included all the 6 cities into the solution. So, the total savings that we have here is 40. Now, what is the solution? Now, this is 1 2 gives us a saving of 16. So, we start from the depot and then we can go from the depot to 1 and then to 2 and back to the depot. This is depot to 1, 1 to 3 and back to depot. So, the solution will be D 2 1 3 depot will be the solution for this. Solution for this will be D6, D5, D5, 6, 4, D is the solution for this. Now 1, 2 and 3 requires a load of 13, which can be met by this 15. 4, 5 and 6 require a load of 14, which can also be met by this 15. So these two are feasible solutions that give us a saving of 40. What is the distance travelled? D to 2 from there is 18, here 1 to 2 is 22, 1 to 3 is another 18, plus 3 to D is another 14. So this travels a distance 18 plus 22 40, 58 plus 14 72. This travels a distance D to 5 is 12, 5 to 6 is 26, 6 to 4 is 32, 4 to depot is another 16. So this is 26 plus 12 38, 40, 70 plus 16 is 86. So total distance of 158 is what is travelled by these two vehicles. Now the savings is 40. If the vehicle had gone individually to each one and come back, it would have travelled 20 plus 18 38, 52, 68, 80, 99. So it would have travelled a total distance of 99 into 2, which is 198. It actually travels 158, which is 72 plus 86. So the saving is 40, which is the same saving, that is 40 here. So this is how the savings based algorithm works, and the algorithm that we have seen is called the Clark-Wright algorithm or Clark-Wright savings based algorithm. Now Clark-Wright is a very effective and efficient algorithm, but Clark-Wright also has its own limitations. In fact, even the limitations can be seen the way we picked up the order. First we could pick 1, 2 and 1, 3 and use up 32, get 32 savings from here, but then the next one we could pick up was only this 5 plus 3. Now several of these savings we are unable to utilize because we have picked up 1, 2 and 1, 3. So it is like a greedy heuristic which tries to initially pick up as much as it can. So it has its own limitations. Sometimes it can give a very good solution, sometimes it may not give us a very good solution. So people try to work better, get better solutions compared to the Clark and Wright, and we will briefly see one of the methods by which we may get a solution that is better than the Clark and Wright solution. So let us do that from here. So let us say we start with S is equal to 0, which means there is no saving. Now the first one from here is 1 to 2 with 16. So we say we use 1 and 2 together. Now saving is equal to 16. Then we use 1 and 3 together. So total saving is 32. Then we used 5 and 6 together. So savings equal to 37, and then we used 4 and 6 together to get savings equal to 40. So the Clark and Wright method gave us this kind of a solution with savings equal to 40. Suppose we proceed from the Clark and Wright by branching here, saying that I am going to create a solution where I am not going to combine 1 and 2 together, indicating it by 1 2 bar, which means I am not combining 1 and 2 together. So right here I have my savings is equal to 0. Now automatically I will start with 1 3, which is here. So I will have 1 3 with savings equal to 16. Then I will look at 2 6. Now 2 6 is possible because 1 3 uses 4 plus 3 7, which is less than 15. Now we could have 2 6, 2 6 uses 6 plus 6 12. So from here we would use 2 6 and get another set of 16 savings, which gives us 32. Then we go to 4, 4 is here, 6 plus 6 12 plus 5 17, it exceeds the upper limit of 15. So we do not include this. Then we go to 3 6, now we have already put 1 3 in one vehicle and 2 6 in another vehicle. So 3 6 cannot go together. Then we get 1 6. So once again 1 and 6 cannot go together because they are in different vehicles. The next one is 3 4. Now 1 3 is 4 plus 3 7 plus 5 12 admissible. So we put 3 4 which with a savings of 10. So we have 3 4 here with a savings of 10. So savings becomes 42, and the last one after that is 2 5, which can give us another saving of 8. 2 5 and 6 adds up to 15. So it is feasible. So 2 5 can give us another saving of 8 and we get a total saving of 50. So while the Clark and Wright solution gave us a saving of 40, branching by saying I am not going to use 1 2 and applying a Clark and Wright again gives us a solution of with savings equal to 50, which means in the original Clark and Wright the vehicles have travelled distance equal to 158. Now in this solution the vehicles would travel distance is equal to 148 because the saving is 50. Here the saving was 40, so distance equal to 158. Now this is also feasible. This gives us a solution 1 3 4. So D 4 3 1 D and D 2 6 5 6 2 5 D, travelling a total distance of 148 against 158, which the Clark and Wright solution gave us. Now the algorithm does not kind of stop here, we need to look at termination of this algorithm. So this is essentially a branching algorithm. One can keep branching in so many ways. For example, from here we can branch by saying I am not going to use 1 3 also, therefore I will start with 2 6 from here with savings equal to 16 and I will use 2 6 to begin with. So like this one can keep branching and keep on branching till we get good solutions. There is no explicit termination condition because in the worst case this will evaluate all possible and feasible savings. So this is an extension of the Clark and Wright method. It is called the Holmes and Parker extension or Holmes and Parker heuristic, which is a logical extension of the Clark and Wright method. So we could use either the Clark and Wright, which is a greedy heuristic, or Holmes and Parker, which is a better heuristic, to try and get solutions to the vehicle routing problem.